Yay, the last video, and that has to be physics. Oh, good. So I get to attempt, as my poor math teacher self, to try to explain to you some physics. So if I say anything wrong, you're welcome to correct me. The other thing that I need to say is that I am going to let you use the notes that are going to be copies that I will copy and paste onto your test when you have to do questions involving work and so forth. And so I can tell you pretty much the different pieces as we go. Maybe I'll backtrack and do all of that. But anyway, Newton's second law of motion is that force is equal to mass times acceleration. The acceleration is acceleration due to gravity. And so that's where you have mass times gravity. And depending on the measurements that you're taking, if you're dealing with metric system, then you have 9.8 meters per second squared. Some books use a little bit different, 32 feet per second squared if you're using the English system. Again, some books have it slightly different, but that's what we're going to use. That's what your calculus book uses. So the first example doesn't calculate work, it calculates force. And so if you have a book that has a mass of 1.2 kilograms and you are going to lift that to a desk that's 7.7 meters high, then the force that's going to be required is for you to take the mass times the acceleration due to gravity. Okay, and so you have to multiply the 1.2 times the 9.8. The height doesn't make a bit of difference as far as the amount of force required to move that thing. Now, if you calculate that 11.6 kilograms per meter times the kilogram meters seconds per second squared, if I could say it. This is a fancy term that they use called a Newton. I guess they're honoring Sir Isaac Newton. By the way, on the Facebook things I've seen, guess when calculus was invented? During a plague. So who's inventing something new now during this pandemic, I wonder? So anyway, our force is going to be 11.76 newtons. Now work is going to be done by lifting the book that we talked about, and that is going to be the force times the distance. So you have 11.76 newtons times 0.7 meters, and you end up with 8.2 newton meters or joules. Okay, and if you're using English system, they use foot-pounds. Now here's the funny part about this. If I told you that the book's weight was 2 pounds, and you lifted it 0.7 feet, so that's the height that you lifted it, then the work that you do is 2 times 0.7, and you'd end up with 1.4 foot-pounds. And so what happens then is you don't have to figure out the force. The force and the mass are the same things in this particular instance. So when you do the English system versus the metric system, it technically, I guess you could say in some sense, it's easier because you don't have to multiply by 32 feet per second squared. It's already been calculated as far as the pounds are concerned. That's how much something would weigh on Earth, and that's taking into account 32 feet per second squared. So if there's an English system, then we don't use the acceleration due to gravity. The force is going to be 2 pounds in that situation. All right, so that's it for this first part. The thing that you would need to note probably would be this, though this doesn't require calculus right at the moment, but that would be something that you might want to make note of that you'll have provided for you with your notes. I'm giving you the notes. You're not bringing your own notes. So let's make sure that that's clear. It's going to be what you're seeing that I'm talking through, and it's going to be some of it, not all of it. All right, so we already did this top part. Okay, you don't need to talk about it. What I need to talk to you about is what happens if your force varies. So the f of x right here is a varying force. So it might mean that at a certain value of x it requires a certain amount of force, and at another value of x it's a completely different number. And so when you have a particle is going to be x feet from the origin, and a force is going to act upon it, how much work is done by moving the particle from 1 to 3. Well, guess what this is? This is the force, and the dx is going to be your distance. And so this product right here is one increment of work. How big is that increment? Well, you're talking about moving it this little infinitely small distance called dx. How in the heck do I get the sum of all of those increments of work? And that's where the integration from 1 to 3 comes in. All right, this is not the clearest picture, but again, there's a copy of this on Canvas. And if there isn't, I will make sure it's one there later. And this is what I'm using to copy for your notes. So this is important, this little part of it, and I will give you that set of notes. All right, now we need to talk about something called Hooke's Law. All I can think of is Captain Hook. If you have a spring, okay, there is a force that would be applied, and that force is going to have a spring constant. In other words, it's going to be proportional depending on the length that it's stretched. And the x is going to be the distance either stretched or compressed from its natural length. Okay, so please be aware that it's not just a number, it's the difference. It's the distance that it goes either to be compressed or elongated or stretched. So if we have a spring that's natural length is 20 centimeters and requires a force of 25 newtons to stretch that spring to 30 centimeters, then what you have then is the force is equal to some constant, and you have to multiply that by the difference in the natural length to the new length, and that's where you end up with this 25 is equal to 10k, and k is equal to 2.5. This is your spring constant, because the force is going to be directly proportional to the length that you either compress or stretch your string. And this is what Hooke's law is saying. So if you wanted to set up the force, it's going to be 2.5 times x. That would be for any of the same spring to extend it past 30 centimeters or compress it down to 10 centimeters or whatever the case may be. So if natural length is 0, 25 is 5 units past. So when we set this integral up, this is our increment of force that we have. The distance is going to be the dx. So when you set this up, here, let me just zoom it out a little bit and highlight it with some different colors here. This is the force, this is your distance, and you're going to have to figure out, okay, the amount of force is going to vary depending on where the spring is at. It's going to require more force the longer that I stretch it. And so when I do that then, how far past the original natural length if I'm going to 25? Well, it's starting at 0 to 25, that's 5 centimeters further. And so I have to do the integral from 0 to 5. And the calculation is, this is Newton centimeters. Move the decimal 2 places, you have Newton meters, and that's going to be in joules. All right, now this is a little bit different, this next example, but it's really the same thing. It says a force is required of 90 newtons to stretch a spring 1 meter beyond its natural length, but they never tell us what the natural length is. Who cares? Because that spring constant is going to be 90 when you calculate that, and you're going to end up with this expression. And so the question is, and it may go on the next page, I guess I ought to check. Yeah, it goes on the next page. We've just figured out that this force is going to be 90x by Hooke's law, and we want to calculate, there it is, we want to calculate the amount of work to stretch it 5 meters beyond its natural length. So that's why it's going to be, for the work, it's going to be 0 to 5 at 90x dx. And if you do that integral and you end up with 45x squared, and you plug your boundaries in there, that's going to give you the 1125 joules or Newton meters. So you're going to have a spring question on your test. So make sure you note whether it's this kind where they give you, go away, where they give you, let me move the picture if I can do this without drawing anything else. They give you that this is the natural length is just 1 meter beyond and 5 meters beyond. You don't need the natural length. And then here you actually had to do the calculations of what the natural length difference was between the extended length so that you could eventually then also use that to figure out how much work was going to be done when you extended that spring 5 centimeters past the original length. So it might be you have to do a difference. It might be that you just simply do whatever the number may be. All right, we have a new kind of problem, and that is you're going to haul up a rope from a cliff. And this rope, and I want a different color, I think brown would be a good choice for rope. This rope is 50 meters long. Now, let's see, how much work will it take if the rope weighs 0.624 Newton meters? So they're telling us what it weighs. So it's like the force, it's like the poundage, except it's Newton meters. And so what happens here, as you pull the rope up, okay, as you pull the rope up, you're going to get, well, let's just say you get X, I want a brown. You pull it up and you coil this around and you got X, okay. How much do you have left from here to here if you coiled that rope around? Well, if the whole thing was 50 and we've coiled up X amount of it, it's going to be 50 minus X. That's how much rope remains hanging over the cliff that you're going to have to lift. So when you go back to this formula then, you have your force and you have your length that you're going to have that's going to vary depending on how much rope that you've pulled up. Okay, and so you have 0.624 times this distance is how much work you're going to have to do at each increment, and we have to multiply that by the dx. And so now, how much do I have to pull up? If I'm going to pull up the entire rope, it's got to go from 0 meters up to 50 meters. And so just think about that a second, if you will. If I'm at 0, then I'm taking a force of 6.624, and I'm going to have 50 dx. That's how much it's going to weigh for me to lift that one little increment of work right there. Because this is the quantity of rope that I have. Now, if I go to 10, let's just say it's at 10, so 50 minus 10, I've got 10 meters up here, so it's going to be that force times 40. And if I get all the way to the top, then that's going to end up being that force right there, and 50 minus 50 is going to be 0 once it's all the way to the top. So if we're not quite there, we're at 49.99999, that's the amount of work that's going to be required. So this is really the entire weight or force, and this is the distance that weight or force is going to be, because it's going to change depending on how much rope you have pulled up or not. So if you calculate that integral, okay, get rid of all my wonderful little things, this is going to work out to be 780 joules. So you hopefully can do integration, so I'm not going to go through that part of it. Now, what if you had a bucket that was going to weigh, what did the bucket weigh? The bucket had a mass of 10 newtons that's attached to the rope. And you're going to have to move that 10 newtons times 50 meters to lift it all up. And so that's going to be 500 Newton meters or 500 joules. So that's going to be an extra amount of work that you're going to have to add to the rope plus the bucket. So I guess if you took those two numbers, 780 plus 500, then you're talking about having 1280 joules of work, and that's the situation right there. All right, now we have another kind of situation where the sand is draining out as you pull this up, as you pull up a bag of sand. So originally it weighs 144 pounds. So we don't need newtons and meters and things like that. As it rose, sand leaks out at a constant rate. The sand was half gone by the time the bag was lifted to 18 feet. Half gone means 72 pounds by the time it's 18 feet. Okay, so that means you're losing 72 divided by 18. You're losing 4 pounds per foot that you lift this rope up. So as you're going, when you first start out, it's 144. For every foot that you lift it, you're losing 4 pounds. And this is the distance, so that is your varying force times your distance. And so again, how much work was done by lifting the sand to 18 feet? The integral is going to be, for the work, 0 to 18, the force times your increment or distance, and that's going to work out to be 1944. Now, when we do a Zoom session, I'm going to do one with an elevator because there's a work problem, and there's another worksheet that I have, and let's see, I think I have a picture of it somewhere. And here it is. This worksheet has all the answers worked out. This would be a great thing for you to work on, to practice all of these things. And I didn't take the full picture of all this because it's on Canvas. There's going to be one like we just talked about that is going to be an elevator, lifting an elevator. And typically I do one of the three when I ask a question: the sand, the rope, or the elevator, and the cable that you have for that. And that would be the third kind that you should be aware of. This one, or this one, or the other one that I'm going to do. Okay, so finally, one last topic to talk about when it comes to work. And I need a sip. And this last thing we're going to talk about, and it is the last thing, and I'm going to have such a good time celebrating tonight because I am done with videos. Sad thing is I've got to do some for Calc 2 as part of the grant stuff, but that'll be more fun because I won't have to do 60 of them. Anyway, we have a tank that has the shape of an inverted circular cone with a height of 10 meters and a base of 4 meters. And it's filled to a height of 8 meters. We're supposed to find the work required to empty the tank by pumping the water to the top of the tank, and the density of water is 1,000 kilograms per cubic meter. So I'm going to take a moment and draw some pictures here for us. Alright, so I've drawn you some beautiful pictures and numbered some things because that's how I roll. I do numbers to figure out the steps of what we have to do here. So what we are trying to do is figure out how much work is necessary to take a tank that is this inverted circular cone and pump it out of the top of the tank. Okay, so we're just going to have it pump outside the edge, and it's just going to kind of just go outside of here. So it just has to get to the top. Now, it's not completely filled. The tank is 10 meters deep, and it is only filled up to 8 meters. And we only have to empty 8 meters of water. So one of the things that I need to do is figure out what the radius is going to be here, and I want a different color. The radius right here. That radius is going to vary depending on this side that is a nice line. Okay, it's a line. Well, how do I figure out what that line's going to be? What I would have to do is recognize that if I draw this as an X and a Y axis that I have done in brown here, this is my X axis, this is my Y axis right here. Okay, then if this point is right here at this location, then it's going to have to be an X coordinate that's 4 and a Y coordinate that's going to be 10 because of the information that we've given and the way that we've drawn that. So I can set up a proportion then that I would have this point that's at 410, and I would have that the ratio of the radius is to 4 as the I'm missing something here. The height, which is going to be y, is to 10. And I'm using y instead of an x, I'll tell you right now. So this setup, I'm going to do it in terms of y. Alright, I think I'm missing something here. Let me look. Okay, I started doing this problem and realized I don't do it quite the way that this is particularly set up. So I'm going to do it another way. So that's what we're going to deal with here. I'm going to do a proportion like I mentioned to you. And that is the radius is to the 4, the outer radius, as the depth of the water is the y is to the 10. Or the height of water is to the 10. Not the depth, but the height of the water. Alright, so when you solve this proportion, you end up with that r is equal to 2/5 y. And so if you want to find the volume, it's going to be pi r squared times the thickness, which it's not going to be what you see here, it's what you're going to see here. My volume is going to be pi times the radius 2/5 y squared dy. That's the thickness, is this dy that you see right here, or here. And I prefer to set it up this way because I think the rest of the setup is easier to follow. But it can be done in more than one way, so both should be giving us the same answer when it's all said and done. Now the mass is going to be the volume of the water times the density of the water, which is 1,000 kilograms per meters cubed. So I multiplied that. I didn't get my calculator out and simplify it, but then the force is going to be the mass times the acceleration due to gravity, which is 9.8 meters per second squared. And then the work that we'll have is going to be the force, which is all of this stuff right here and here, times the distance that the water has to be pumped out. Now, the distance that it has to be pumped out is this distance right here. I shouldn't call it the depth, I should call it just d. Alright, so that's just scribbled too much. We'll just leave the d right there. Alright, so any strip of water that you have has to move that distance that you see d is, and that distance is going to be the difference between the total distance 10 and the distance that is the height or the depth of that representative rectangle that you see right there. So the depth is going to be 10 minus y. So this is the one increment of work. If you want to find the sum of all those increments of work, then you have to do what? Well, it has to scan from 0 to this distance, which is an 8. And it makes sense with this depth, as I'll remind you when we get to the end, and that is, if it's at the very tip top, it has to move 2 meters. If it's at the very bottom, it has to move 10 meters. And that's what this depth right here represents. So the answer, let me leave this for a few seconds here. The answer that we would have, as far as setting this up, would look like this. We would have to integrate that from 0 to 8 so that we could get the sum of all those little slices of water that we're going to pump out of that tank. And I'm guessing we're going to be talking about this when we do a problem later, and I'm going to do it just like this. Alright, so maybe I have to reevaluate the notes that I give you. Here's another example, and again it looks like it's done with the dx, and I may have to write up the notes a little bit differently here. So the setup is going to be very similar, except we have the weight is 57 pounds per cubic foot for olive oil, and it has another inverted conical tank that has a height of 10 feet, so it's the same height. The base radius is 5 feet. That's different, and it's only filled within 2 feet of the top. That's the same thing. It's filled up to 8 feet. So if I was to do my similar triangle here that I did before, if I just focus in on that, this is 10 and this is 5. And then I have my representative rectangle right here, and this is the radius that it is there. And this is going to be a y distance when I do this on the x and the y axis again. So what I'm trying to get you to realize here is that I'm going to set it up. Oh, olive oil ought to be this color, I think. We have this conical tank. We're setting it up like this, and it's only going to be filled up to 8 feet. Or 8 feet. So this is 5 feet, and this is 10 feet, and this is 8 feet right here. So I'm going to set this up in a similar way that we did a moment ago, but I want to explain this part of it. 5 is to R. I need a different color. 5 is to R as 10 is to Y. And so if I cross multiply, 5Y is equal to 10R. Divide by 10. Hi puppy. All right, so I have R is equal to 1/2 Y. So when I set this up, when I do the volume, I'm going to have pi times the volume, which I think I'll just write it as y over 2 squared dy, because this is, again, one of these discs that you see right here. And this is the representative rectangle that is associated with that. When I do the force, okay, I'm going to have the volume times the weight. I don't need to do anything excessive here, so pi, I can go ahead and simplify this. Pi times y squared over 4 dy, and then the density is going to be 57 pounds per cubic foot, and I'm not going to worry about the different units here. And then I need to figure out, let's see, that was the force. So the work that I need, okay, I don't need to do that extra step like we did in the last one. I'm talking about this extra step with the mass, and then figure out the force. We can bypass this step. So the work is going to be whatever the heck, 57 pi divided by 4 y squared dy. I'm going to leave it like that. And then the distance. Well, the distance is going to be very similar. If this is y, then this distance is going to have to be 10 minus y, that it's going to have to be pumped out. And so if I want to figure out the total work, that's what this is, total work, I'm going to have an integral, and I'm telling you right now it's going to be from 0 to 8, just like the last one, of 57 pi over 4. Why is it 13? Oh, wait a second. No, I messed it up. All right, we're supposed to pump this 3 feet higher than what we started out with. That's my problem. So the thing that I have to change is just this right here. This needs to be 13 minus y is the distance that it has to be pumped, because this is 13. And if this distance is y, then the distance that it has to travel is going to be from here to here. So let's go back to the black here. And I would have 13 minus y dy, and that would be my setup that I would have for this particular integral right here. And again, I would much rather do this, I think. Oops. I would much rather do this if I could underline it without destroying anything. And we will get the same answer. But I've got to make sure that everything does what I think it's supposed to do. When I'm at this point right here, let's change the color to that blue or something. When I'm at this point, the highest point where this is filled up, it has to go how far? Well, if I do 13 minus 8, it's going to go 5 feet. And when I'm at the very bottom, how far is it going to have to go? And it's going to be 13 minus 0. Yes, it's going to have to go 13 feet, because we're pumping it 3 feet higher than what it started out to be. Okay, I have a couple more that I wanted to show you. It's more the volume part of it than anything else. And I need to take a sip. So count to 3. Pause it if you want. This is how I'm going to explain it. If I have to, I guess I have to rewrite the notes again that look something like this and scan that part of it. Alright, I already showed you that picture. What I wanted to show you is a situation where you're going to fill a trough with water. Now, some of you don't watch cowboy movies, and that's just a real sad state of affairs. But troughs are when they would fill it for the horses so they could drink the water. Okay, so we want to calculate the amount of work it would take to empty one of these troughs. Okay, and so if I do my representative region right here, then we're trying to figure out the volume of one of these. And it's just a rectangle. As fancy as I can draw it here, it's just a rectangle. The part that's going to be the challenge is what in the heck is the width? And I'm talking about this part right here. So it's going to turn out, how well do you remember your algebra or your geometry? That's what it's going to turn out to be. Now, if this is an isosceles triangle, and that's what I've got drawn here is an isosceles triangle. And that means that the two sides are the same. Okay? And the other side, whatever it may be, well, we have to figure that part of it out. But we do know that these two angles are 45 degrees. So if I just made up a measurement that this height of this trough, for instance, let's just say it's 10 feet. Or the width of this trough is 10 feet. And let's say the length is 20 feet or 25 feet. I don't really care. What we have to do to set this problem up is we've got to remember our geometry. I've drawn this so there's symmetry. So I don't want this whole triangle. I want that this is going to be 5 because it's half. I've drawn it so it's symmetric. And if this is 45, this is also 45. And this is going to be my right angle in this case. And so what does that make this measurement? It's going to be a 5 as well. And so what's this going to be? Well, this is going to be 5 to the square root of 2. Do I even care about that? And honestly, no, I really don't care about this. Because I'm going to have my representative rectangle go all the way across right here. That's this measurement right here. Okay. So I want to get this entire length that you see. So I have to come up with some kind of equation that would describe this. So if I'm at the point 5, 5, because I went 5 up and 5 over, I think it should be pretty darn obvious that the equation of the line that connects this is going to be y equals, if you do the change in y over change in x, it's going to be 5 over 5x plus 0 because it goes right through the origin. And so that's what that equation is. Y is equal to x. So what I hope that you realize is that this distance from here to here, that is going to be the same thing as y equals x, or vice versa. So the entire distance is going to be, from here to here, it's going to be 2y, or it's going to be 2x, whichever way you want to set it up. And I know which way I want to set it up. All right, I forget what it is for water, so I guess we'll just use olive oil again. But if I want to find the volume of this rectangular solid then, I know that this width is going to be 2y. So I'm going to have 2y. I'm going to have a length which is going to be 25 feet. And my thickness is going to be dy. That's my volume. So if you want to clean it up, it's 50y dy. Alright, so then I need to figure out the force. And if we use the olive oil, it's going to be 50y dy times the 57 pounds per cubic foot. And I really don't want to multiply that. I'm just going to rewrite it as 50 times 57 y dy. So 1 increment of work, well, I have to figure out how far this has to be lifted. And if the whole darn thing is going to be full, then this distance right here is y. The entire distance is 5, so this distance is going to have to be, well, guess what it's going to be? It's going to be 5 minus y. So when I integrate this to get the total work, I'm going to have the integral of, and I can tell you it's 0 to 5 if it's full. I don't even have to think about that. Whatever the heck 50 times 57 is, which I don't care. And then I'd have y times 5 minus y dy, and there's my setup. Okay, so that's what you need to do in that particular situation, is remember your geometry about a 45, 45, 90 degree triangle, which all of my 28 or 9 trig and pre-calc students should remember. Now there's one more I need to show you, and then I'm going to celebrate. Alright, here's another picture, and it's a parabola at the ends of the trough, and the parabola has this set of boundaries that I've drawn for you. It's not the best parabola I've ever drawn in my life, but it will do. Again, this is my representative rectangle, but it actually goes further than that. It goes this entire distance. But I want to figure out what this measurement is to help me figure out what this is going to be for my length. So what I'm trying to tell you is the parabola has this equation, y equals 1/9 x squared. Guess what I'm going to need if I'm going to have this all in terms of y? I need to have this solve for y, or solve for x in terms of y. And so I did that somewhere, didn't I? No, I haven't done it yet. Okay, you lazy bum. Multiply both sides by 9, take the square root, and now you're talking 3 the square root of y is equal to x. That's one side of it. I don't really want to do right minus left, though I could. It's just going to be double that amount. So let's go back to our black colors now and talk about it. And since, again, I'm not sure of measurements here, let's just say it's in feet, and we'll do the olive oil again. So when I do this, it's just going to be a nice little rectangle. Let me show you what I'm talking about. Let's suppose that this is 15 feet, and we're talking about this rectangle right here. So if I want to find the volume of that rectangle, it is going to be whatever the length is, 15, times whatever the width is, and we just decided that this width from here to here is going to be 6 the square root of y, because we're doubling that radius. Now, it's not a rotation like it was for that cylindrical cone, inverted cone. It's just going to be 6 the square root of y, and then I'm going to have the thickness, which is dy, and that's just too easy to simplify. That's just going to be 90 the square root of y dy. And the force is going to be this number, the volume, times that, if we do olive oil again, the 57 pounds per cubic feet. And the only reason I'm doing olive oil all the time is I don't want to get up and look at what it is for water. I think it's 64.7, but I don't care if I remember that or not. So 1 increment of work. Well, I have to know that this distance is 9. Well, I had that. I didn't have to do anything fancy. So I know that if I pump this out, if this is y, then my depth, distance that I'm pumping it, is going to be 90 times 57, the square root of y, dy, and then the depth is going to be 9 minus y. So the total work, and again, this trough is full, the total work is going to be the integral from 0 to 9 of whatever the heck 90 times 57 is. And then we'd have the square root of y times 9 minus y dy, and that would calculate the total amount of work to pump that water out. Alright, so I'm going to go to all of these three things that I've shown you and make sure that you can copy it down if you want to. And this is how I'm going to set them up. You can do it other ways, but this is what I'm going to do. Alright, counting to 3. I'm going to count to 3 to this one if you want to pause it. Counting to 3 to this one if you want to pause it. Counting to 3 for this one if you want to pause it. And if you want your final answer, that's on another slide, so let me find that other slide. And there's the answer to that one that was in brown. So I hope you're able to pause it, but I'm about to celebrate because I am done.